Hey there, and welcome to the Coding Ikigai. I'm Harsh, a software engineer at Oracle, and I'm on a mission to help you find your niche, your Ikigai in the world of programming. You're about to dive into the core Java programming series, a completely free, in depth guide designed to know everything there is about the Java programming language and to get you industry ready. So let's get started. This is Episode 3, Part 2, Conversions and Context, a guide to expression evaluation using the rules of data type conversions, along with an introduction on statements in Java. And you are watching a series of such episodes to gain a deeper understanding of the Java programming language. I have broken down this episode into multiple chapters. So if you're already familiar with the topic, just go ahead and jump to the next one. If you missed any of the previous episodes, you can check out the complete Core Java playlist linked in the description down below for a detailed understanding. CCC Nagini. In the first part of this episode, we discussed how precedence and associativity of operators influence the overall outcome of expression evaluation. This episode will expand on the concepts introduced in Part 1. So if you have missed Part 1, you can find the link to that video in the suggestion above. With that in mind, let's proceed with Part 2 of Episode 3. Context refers to different types of scenarios and situations in which you can use your expression in a program. Each context has certain different rules for handling expressions and producing the final results. There are 5 contexts in Java: numeric context, casting context, assignment context, string context, and invocation context. Try to remember these contexts. We will come across them in a lot of episodes. In Java, we already know that every expression finally results in a single value of some data type. Let's call that data type as source data type. Depending on different usages or context of your expression, that source data type may need to be converted into another data type. Let's call it as target data type T. The process of converting a data type from source data type S to target data type T is known as data type conversion. In Java, there are 12 possible data type conversions. In this episode, we will primarily focus on 4 of these conversions, as we haven't covered the necessary concept for the remaining ones yet. We will introduce the others as the series progresses and the relevant topics come up. These 4 conversions are identity conversion, widening primitive conversion, narrowing primitive conversion, and widening and narrowing primitive conversion. To begin with casting context, a casting context occurs when the value of an expression is forcefully converted from its original source data type to a target data type using the cast operator. The syntax for the cast operator is the target data type in parentheses followed by the variable name or the value that you want to cast. For example, if the value of an expression is 29.45, which is a double literal, the source data type is double. Suppose we want to forcefully convert it to an int. Simply place the cast operator with int as the target data type in front of 29.45, and voila, it converts the value to 29, which is of int data type. Now consider another example where d is a variable of type double, and we want to convert it to an int again. Just use the cast operator with int and it will do the job for you. Remember, casting does not change the original variable or value. It always returns a new value on top of it. For instance, after casting, d still remains 29.45 and not 29. In a casting context, an expression can go through any of these 4 data type conversions. You can see that with a green tick on top of all the boxes. There are a lot more conversions which casting context support, as you can see in this particular image. But once again, keep in mind that for this episode, we are focusing on a narrowed version of data type conversions. The other conversions will be introduced and added to these contexts as we cover them in future episodes. So let's understand all of these 4 conversions with examples in casting context. A conversion from a source data type to the same target data type is called identity conversion, meaning S is equal to T. Let's look at some examples of identity conversions in casting context. For example, here the literal 2945 is of type int and is being cast to the same int type, returning 2945 with no change. This is an identity conversion. In the second example, the double literal 29.43 is casted to double, returning 29.43 without any change. Similarly, in the last case, var, a variable of long data type storing 294, is casted to the same long type, and again it returns 294 with no change. So that is an identity conversion. A type conversion that occurs when a smaller primitive data type, the source, is converted to a larger primitive data type, that is the target, is known as widening primitive conversion. There exist a total of 19 possible widening primitive conversions in Java. Let's look at each of them one by one. First, we have is widening primitive conversions from byte to either short, int, long, float, or double. All of these conversions are lossless, meaning no information or bits are lost during the process of conversion. For example, consider a byte variable var holding the value 32. In the first case, the byte is widened to int through casting, returning 32 basically, but of the int data type. It's a lossless conversion. In the second case, var is widened to float through casting, returning 32.0f, a float data type at the end. Finally, in the last case, var, which is a byte, is widened to double using casting, returning 32.0, a double data type at the end. Easy, right? Next, we have is widening primitive conversions from char to short, int, long, float, or double. All of them are lossless. For example, consider a char variable var holding a. Since characters maps to integers when casted to int, it basically returns 97, an integer literal. When casted to long, it returns 97L, a long literal. In the third case, it returns 97.0 because it is being casted to a double type, which is a double literal. Next, we have is widening primitive conversions from short to int, long, float, or double. All are again lossless. For example, consider a short variable var holding 68. When casted to int, it returns 68 again of the int data type. When casted to long, it returns 68L, a long data type. When casted to double, it returns 68.0, a literal of double data type. Similarly, we have widening primitive conversions from int to long, float, or double. Note that converting int to float can be lossy in nature. For example, consider an int variable var holding 321. When casted to double, its value remains same, that is 321.0, but it is a literal of double data type. However, when the int value is too large, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, converting it to float can cause a loss of precision because the floating point data type has certain limitations. A float can accurately handle only up to 9 significant digits, which leads to a mismatch in the last few digits, as you can see in this particular example over here. Despite this, Java still attempts to perform the conversion, though some data is lost during the process. This is called a lossy conversion. Next, we have is widening conversion from long to float and double, both of which are lossy in nature. For example, when the long literal 324L is casted to float, it correctly returns 324.0F in the float type. However, when dealing with larger values again, such as long variable var holding 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8L, which is a too huge value, casting it to a double results in a loss of precision because the double data type again cannot accurately represent more than 17 significant digits. And finally, there is the widening conversion from float to double, which is also lossy in nature. For instance, when a float literal 12345.6789f is casted to double, some information is lost during the conversions. The reasons behind this loss of precision are beyond the scope of this discussion. Here is a summary of the formal behavior associated with widening primitive conversions. For further details on this topic, I have included an article on conversions and context in the description down below, which you can refer for more information. Reverse of widening primitive conversion is narrowing primitive conversion, a type conversion that occurs when a larger primitive data type, that is the source, is converted to a smaller data type, that is the target, is known as narrowing primitive conversion. There are 22 possible narrowing primitive conversions in Java, and all of them are lossy in nature. First, we have narrowing primitive conversions from short to byte or char. These conversions are lossy because when moving from a 16-bit data type to an 8-bit one, let's say, then Java effectively discards 8 bits of information. So that is why lossy. For example, if a short variable var holds the value 200, casting it to char results in 200 as well. However, the output is its corresponding Unicode character, which is E with a grave accent. When var is cast to a byte, it loses data and returns minus 56. In narrowing conversions, the n lowest order bits are retained, which is in this case 8, while the rest are discarded. In this case, only the lowest 8 bits are kept and the rest are thrown away because the target data type is of 8-bit size. Next, we have narrowing primitive conversions from char to short or byte. These conversions are also lossy for the same reasons. For example, consider a char variable var storing the character a, which maps to the integer value 65. When cast to short or byte, the integral value 65 is returned. Pretty easy, right? Next, we have is narrowing primitive conversions from int to short, char, or byte. These are also lossy in nature. For example, if an int variable var holds the value 1, 2, 3, 4, 5, 6, casting it to short returns minus 7616. Similarly, casting the integer literal 292 byte results in 34. The reason for this discrepancy is the same. Only the n lowest order bits are kept, while the rest of them are discarded. Next, we have is narrowing primitive conversion from long to int, short, char, or byte, which are again lossy in nature. For example, when a long variable var holding 1, 2, 3, 4, 5 is casted to short, it returns 1, 2, 3, 4, 5 because it falls within the range of short data type. However, when a very large integer value is narrowed down, it loses information during the conversion, as you can see in the second case, resulting it in a negative number. Next, we have is narrowing primitive conversion from float to long, int, short, char, or byte, which are again lossy in nature. When a float value that is too large to fit is narrowed to an int, it returns the largest possible int value that can be stored inside the int data type. And if the float value is too small to fit, it returns the smallest possible int value, as shown in the first case over here. In the second case, a float literal 23.47f, which is within the integer range when casted to int, loses the fractional part or the part which is written after that decimal point, returning only 23 as the final answer. Lastly, we have is a narrowing conversion from double to float, long, int, short, char, or byte, which all of them are again lossy in nature. This works similar to float conversions, but in double to float narrowing, if a double value is too large to fit inside a float, it returns infinity. That is a predefined constant in Java representing a very large float value. If the double value is too small for float to accommodate, it returns 0, as you can see in both of these examples over here. These are the formal set of rules that narrowing primitive conversion follows. You can pause the episode over here and read it for more details. In Java, converting a byte to char first widens the byte type to the integer data type and then narrows it down again to char, which is quite an uncommon process. For instance, when a byte variable var storing 65 is casted to char data type, it first becomes an integer and then narrows it down to return the Unicode value A again. However, if var holds minus 100, let's say, casting it to char results in the Unicode value at 65,436, as characters are always positive and the sign is discarded during the narrowing down from int to the char data type. So that was all about casting context in Java. We have seen all the different kinds of conversions that are supported in the casting context. Numeric context refers to situations where an expression is used in a numeric operation like addition, subtraction, multiplication, division, and so on. It applies to the data type of the operands, which is the source, in an arithmetic operation. Numeric promotion refers to the process of converting operand's data type to an inferred target data type to fit the result. For example, in this expression over here, with different data types like int, float, and double, how do we exactly solve it? Let's find it out. In numeric context, only identity and widening primitive conversions are allowed. The rest of the conversion, that is 3 and 4 over here, are not at all allowed. The rules for evaluating an expression with multiple data types in a numeric context are simple. If either operand is double, the other is converted to double data type. Else, if either operand is of float data type, the other is converted to float. Else, if either operand is of long, then the other is converted to long data type. Otherwise, both of them are converted to int. So, byte and short and char are automatically promoted to int or higher data type depending on the context. For instance, in this expression, the multiplication happens first due to higher precedence over the equality operator, and obviously because it's in brackets. But the operands around the multiplication have different types. So the int value 2 undergoes numeric promotion to float, becoming 2.0. The multiplication is then evaluated, which returns 8.0f. Next, the operands around the equality operator also have different data types. So 8.0f is promoted to double based on the rules of the numeric context, resulting in 8.0. Finally, the evaluation happens and it returns false as the final answer, which is a Boolean literal. Next, let's consider integer division. We have already seen this before, but here's the reasoning. When dividing 10 by 4, both operands are literals of data type int. So the final result is also of int data type. The fractional part in 2.5 is lost while narrowing it down to int, leaving just 2 as the final result. However, when we divide 10 by 4.0, then according to the rules of numeric context that we just saw, since one of the operand is of double data type, 10 will automatically undergo numeric promotion or widening primitive conversion from the int to double data type, and final result is 2.5 with double data type. Hence, the difference between the two types of integer division. Unary operator rules are simple. If the operand is of byte, short, or char, it widens to int. Otherwise, no conversion occurs. For example, with b as a byte type variable, applying negation to it widens it to the int data type according to the rules of unary numeric context. But for variable a, which is of long data type, no conversion happens. In numeric context, Java automatically applies identity and widening primitive conversions, also known as numeric promotions, to any expression used within that context, according to the predefined rules of numeric context for binary and unary operators. So that's it for the numeric context. Assignment context is an occasion where an expression is used for assigning a value to a variable. The type of the value of the expression is the source, and it must be converted to the data type of the target variable in which we are trying to store it, which is t in this case. If the type of the expression s can be converted to the type of target variable t in an assignment, we say the expression is assignment compatible with the type of the variable. For example, here in this case, we are assigning the expression whose final data type is float to a target variable var1 with a double data type. Can a float be converted to double in assignment context? Let's look at all the supported conversions in assignment context. In assignment context, only identity and widening primitive conversions are supported, and in some cases, narrowing primitive conversion is also supported. Let's begin with identity conversion in assignment context. The rules of data type conversion remains the same across all types of context. For instance, when you assign the double literal 2.0 to a variable of type double, it goes through an identity conversion from double to double, storing 2.0 in var1. Likewise, assigning the value 3245L to a long variable undergoes the same identity conversion from long to long, ultimately storing it inside var1. Simple, right? When you assign the int literal 2 to a double variable var1, it undergoes widening primitive conversion from int to double data type, becoming 2.0 and then getting stored in var1. Similarly, if an int variable var storing 1 to 3.56 is assigned to a long variable var1, it undergoes widening primitive conversion from int to the long data type based on the rules of the assignment context. These are just two examples out of all the 19 possible widening primitive conversions in Java, but that is just for the sake of understanding. Narrowing primitive conversion in assignment context. Narrowing primitive conversion in assignment is allowed only when this condition holds. If the expression is a constant of type byte, short, char, or int, that is the source, a narrowing primitive conversion is permitted if the target type is byte, short, or char, and the constant's value fit within the range of the target data type. In this case, we are trying to assign a literal of data type int to a variable var of byte data type. So it's a narrowing primitive conversion. Let's see whether it's allowed in Java or not. Java will allow the narrowing primitive conversion on 42 from int to byte data type because 42 is a constant expression with source type as int and target data type is byte. And 42 is also within the range of byte data type. So it fulfills all the conditions that we talked about. However, assigning a variable var of data type int to a variable s of data type short will throw an error because var is not a constant expression in Java. Similarly, assigning literal 425 to data type int to a variable b of byte data type throws a compile time error because 425 is out of the range of target data type byte. We know that the range of byte data type is from minus 128 to 127. That is why it violates the constraints of the conditions that we have put above, and hence it will throw an error. And that's all that you need to know about conversions in assignment context. In a string context, an expression is combined with a string using the concatenation operator, converting the expression's value into a string data type. For example, my age is 30. Here 30 is a literal of data type int, but it undergoes string conversion and gets itself converted into the reference data type string. More details will be discussed in future when we will talk about strings and concatenation operator, and then we will talk about string context. Invocation context occurs when an expression is passed as a value to method or constructor parameters, leading to type conversions. For example, in this case over here, passing 12 and 13 to a method m that takes two parameters of double data type results in widening conversion of 12 and 13 from int to double data type. We will cover more on this when we will learn about methods in future episodes, and then we will learn about what all data type conversions are supported in invocation context. Now that we understand precedence, associativity, type conversions, and context in Java, let's solve a miscellaneous expression comprising of different operators and different operands of different data types using our two-step process. Step 1, bracketization. The expression involves four operators: addition, multiplication, a cast operator, and division. According to operator precedence, the cast operator has the highest precedence. So we place blue brackets around it. The next highest precedence is of multiply and divide, but both share same precedence. So how do we break the tie? Using associativity. Since they are left to right associative, multiply will happen first. So we place turquoise color brackets. Next comes divide, so we place pink brackets around it, and in the end, addition has the lowest precedence, and that will be evaluated at the end. Step 2, evaluation and type conversion. As we can see, multiple data types are involved like int, float, and double. Here we will use the concept of type conversions and context. Starting with the blue brackets, we perform a cast operator on C. As a result of this, the variable C undergoes narrowing primitive conversion from double to int data type in casting context. Hence, the value 2.5 inside C converts to 2 of int data type. Next, we evaluate turquoise brackets. Since variable b and 2 are of int data type, we can go ahead with evaluation of multiply without any data type conversion. So b multiplied 2 gives us 10. Next, for the pink brackets, the data type of operands is different for division operation. One is int and another one is float. Hence, 10 undergoes widening primitive conversion from int to float data type according to the rules of numeric context and becomes 10.0f of float data type. Since both operands are now of the same type, we perform the division, which results in 5. Finally, the addition operation remains. As the operands are of different data type, the variable a undergoes widening conversion from int to float. We can then perform the addition, which returns 15.0f of float data type. However, since the result is stored in a variable of type double, the value 15.0f, which is of float data type, undergoes widening primitive conversion from float to double in the assignment context. And that's how we solve and evaluate any general Java expression. Voila. Expressions cannot exist as standalone entities in a Java program. If you try to do that, Java throws an error of not a statement when we try to execute expressions directly. The smallest unit of execution that a Java compiler can process is a statement. Statements are like a group of words that make complete sense to the compiler. Statements are roughly equivalent to sentences in English language. A statement forms a complete unit of execution and is always terminated at the end by a semicolon. Remember that. There exist three different statements in Java: expression statement, declaration statement, and control flow statement. Expressions that can be turned into statements by ending them with a semicolon are called expression statements. There are three types of expression statements. Assignment statement. These are assignment expressions that end with a semicolon, like assigning 28.43 to the variable avar, or assigning an expression to a variable var, both followed by a semicolon. Then we have increment and decrement statements. These are prefix or postfix increment decrement expressions like avar plus plus, avar minus minus, followed by a semicolon. And at the end, we have method call statements. Example includes method calls like system.out.printlnewline with a welcome string in the between, or method call with two arguments arg1 and arg2, which are basically expressions that ends with a semicolon. A declaration statement declares a variable along with its data type. You have seen many examples of this. For example, int a followed by a semicolon declares a variable named a of data type int. Or in the second case, we are declaring a variable named avar and assigning 28.43 to it. So that is declaration along with initialization. And all of them ending with a semicolon, representing that they are statements. Control flow statements dictate the sequence in which statements are executed. When you write a program, statements are normally executed in order they appear in the file. That is, from left to right, top to bottom, without any interruptions. For example, take this program that calculates the area of a circle. The lines are numbered 1 through 6. In the simple flow, the program starts at line 1 with the main method and runs sequentially through line 6. That is 1, 2, 3, 4, 5, 6. However, when you add control flow statements, the execution path changes. For example, consider a program that calculates the area of a circle only if the radius is non-negative. The program runs as expected from line 1 to line 4, that is 1, 2, 3, 4. But after line 4, the flow splits. If the radius is negative, the program jumps to line 5 and then directly jumps to line 8 without calculating the area of the circle and ending the program. Otherwise, it moves from line 4 to line 6 and 7 and then ends at line 8, calculating the area of the circle. These are the list of control flow statements in Java, and we will understand them in detail in the next episode, Take Control of Thy Flow. Oh, that was an elaborate discussion on expression evaluation. But now, with everything covered, you will never need to consult another resource on this topic. We have got you fully equipped. To summarize, expressions are valid combinations of variables, operators, and method calls that always return a single value of a specific data type. Expressions are evaluated according to precedence and associativity rules in Java. When an expression involves different data types, it is first converted to a compatible data type based on the conversion rules for that particular specific context in which that expression is getting used. Finally, statements represent complete units of execution in Java, and a collection of statements together form a program. And that's it for this episode. In part 3 of this episode, we will talk about how can you control the flow of your program using selections and loops in Java. With this, we have covered the fundamental steps in understanding the syntax of Java programming language. You are now familiar with the character set, variables, data types, operators, expressions, precedence, associativity, data type conversions, context, and statements in Java programming language. We have learned a lot of things. So thanks again for watching. If you enjoyed the animations and the content, please consider giving this episode a like. It really helps the channel grow. And if you want to see more content like this from me, don't forget to hit that subscribe button and ring the bell notification so that you never miss out on an update.